Let's see, if I start talking, you can hear me now. Great, thank you. Hey everybody, welcome. This is the February 25th. I think we're going to start the way we often do with a bunch of different thank yous and announcements before we get to tonight's speaker. The first, as we usually do, we need to thank Angeline and the staff here at the Belfry who get us here every third Tuesday. And in between third Tuesdays, they do so many other things, some art and music events here that just make Sisters one more way. Sisters is a wonderful place to live. I'd also like to thank our board, who I think many of whom, not all of whom, are here tonight. To start off with David Dern, our president. He'll be back up in a moment. Don Utzinger, I think, is up in the back. In addition to being our vice president and treasurer, Don has become our videographer and has been posting a lot of recent lectures to our website. So if you missed something and you want to look at it again, or you want to study it in greater detail or send it to a friend, you do all those things. And on that website, you can also see past, present, and future lecture series coming up and other activities on behalf of the club. So thanks to Joe Sherry, who's here tonight, and right over here, and Jocelyn Blevins for helping get the website up and going. And while I'm on the topic of Jocelyn, who is the STEM teacher at our brand new, beautiful elementary school across town. And she has an event going on in 2 days. That will be Thursday the 27th, but you just remember 2 days so you don't forget it. STEM night at the elementary school. It is a blast. And if you haven't been, your taxpayer dollars paid for it, to the new elementary school, you should go over there and see it. There's no admission fee. And you get to see a bunch of charismatic young scientists at work. And you can help Jocelyn, who needs a few more volunteers. So Jocelyn, raise your hand again, and on her computer, she can type your name and contact information and put you to work doing something helpful and useful on Thursday night, and I guarantee you will have fun. So, thank you. Also, Dave Johnson, I think, is here. I'm just still running down the board. Larry Price, David Ellis is not here. David and Joe Sherry, who I mentioned, Larry's right here, have been, among other things, Larry's been a recent speaker, but have also been lining up the other speakers, including tonight's, for the Frontiers in Science lecture series. So if you know a terrific speaker that might want to come and address an audience like this here in Sisters, please let Larry, David, or Joe know. Gail Todd is not here tonight. Normally I would thank her for doing so many of the logistics and the communications. She has been a really tremendous link between the club of a couple years ago and keeping it going and alive and dynamic. Gail's not here tonight, but the other part of the announcement that I make is that the newest member of the team, not a volunteer board member, but is working with Gail and Larry and David and Joe, is Dana, and I forget your last, Dana Greenblatt. Thank you, there's Dana right there. He's going to be handling a lot of communications and helping the speakers be effective and etc. Karen Schweigert and Ann Richardson welcomed you at the door and took your donations. Thanks for that. I understand that Dana McNeese helped set up all these chairs, and if you're willing to please help unset them, that would be fantastic. Peyton Myrie in the back was hired as the audio guy, and if you've been here for the last few lectures, we know he's also a pretty darn good video projection troubleshooter guy, so thanks also to Peyton. One more quick thing I'll say, and then ask David to say a few words, is that our next speaker is Dr. Elizabeth Safran from Lewis and Clark College up in Portland. The topic for her lecture is Cascadia Subduction Zone, and the big one that is coming. And I recall, and many of you in the room might also recall, that several years ago we hosted a Frontier in Science lecture with Danielle McKay, who's been back since, but she was from the U of O talking about the Cascadian subduction potential for an earthquake. And in fact, what we should all be doing to prepare in terms of safety. That was 7 or 8 years ago, I think, at this point, and still no quake. So that pressure is building up, and it's probably time for a little refresher. So please mark your calendar. It's going to be on the 25th of next month. And David, I think, why don't you come up and explain what's happening also in April.
Come around this way today. Yeah. It's built so I can get out there.
Good evening. I'm David Duran. As mentioned, I'm the president of this club. One of the missions that we're trying to do here in Sisters is to help the teachers raise money for some of the trips and some of the science activities that happen that isn't funded by the district. And so as a result of that, we're going to hold a fundraiser on April 27th, Sunday afternoon. You've seen the slide, it's going to be up at 5 Pines. We hope you could join us, we hope you can be generous. That's all I have to say for now.
What are we going to do besides give you money?
Thank you, thank you. Just a couple thoughts before we get to introducing our distinguished speaker for tonight. Here's a question for you. Do you have weird dreams? You know, I was in an audience not long ago, and the speaker asked that in a question, and all the people around me started muttering, I had this dream last night, I was in the Old West, or I was, swimming around in a kelp bed, and this cyclops came up and started talking to me in Portuguese and all this, and that whole time I'm sitting there thinking, nope, I don't have, it's like if I'm lucky enough to remember a dream at all, it's like, it requires no imagination to make the whole, there is no imagination. It's exactly, my life in my dreams is exactly the same as my life in real life. And I don't know exactly what that said, but did kind of some data collection on this. A number of years ago, I was working in Silicon Valley, helping run a little company, and at the time we had about 50 people on our development team. About half of them were PhD scientists, the kind that can see around corners and have great ideas. And the other half were really skilled engineers in a variety of vertical domains and really good at what they did. And my job was just, going to meetings all day and trying to, talk to investors and engineers and strategic partners and trade press and whatever, just keep the wheels all spinning. And I'd go home at the end of a 10 or 12 hour day, just tired. But then by the time I'd hit the hay, I'd have another 6 or 7 hours of just the same stuff I'd been doing all day long. And it was just like, come on, give me a break. I'd love to fly around on a giant pizza and a kangaroo that, looks and sounds like John Lennon or something weird, And that just never happened to me. These dreams, anyway, I could keep going on, but it was just basically another work day all night long. And so I remember, though, one time I was at work talking with a few workmates, and somehow the topic of dreams came up, and several of them were saying, I keep having these weird dreams where all this freaky, surrealistic stuff happens. And then a few of us were like, no, we just have boring dreams. And we realized it was the scientists that had the surrealistic dreams, and the engineers had the really boring ones. And I don't know. So we started going around. It was like we had 4 data points or 5, and we started going around and asking all these people. And sure enough, we started developing this correlation. So you develop a theory, and the theory that I still remember today is that these crazy, vivid dreams are to monotonous dreams the way that scientists are, the engineers are. Put another way, creatively inspired insight is to careful systematic analysis, or big picture breakthroughs are to the kind of relentless incremental progress toward a specific goal. All right, at this point I'm just going to say I don't know a dang thing about dreams, and I don't know, this whole thing could be complete baloney, I don't know. But I did notice that correlation, and I gotta say, when we had Mark Pitzker here not too long ago to talk about the human brain and dreams, we should have asked him then, and if he comes back, I will ask him then. But finally, here's the point, is that if the history of science, at least to me, shows us anything, it's that scientific understanding and technological development are both those fields are sort of equally driven by the two types of thinking, the two approaches to thinking that I was just describing, you know. And if we want to decode nature and better understand the mysteries of the universe, or, you know, develop new technology that'll help improve people's lives, we really need both ways of thinking, you know. It's punctuated, you know, development is punctuated by incredible brilliance, but then a heck of a lot of hard work. And as a broad topic, I could think of no better exemplar of that sort of duality than the topic for tonight, which is mass spectrometry. And, you know, the history of the mass spectrometer goes back to the early decades of the 20th century. And the development of the mass spectrometer itself is a story, you know, that is, in fact, creative genius and sustained tenacity in the lab. But then also the myriad scientific and technological breakthroughs that have resulted from its use as a tool also exemplify, you know, that interplay between inspired insight and dedicated engineering effort. So, and I think as tonight's speaker will attest, the applications for mass spectrometry today are revealing insights into the atom all the way out to, you know, understanding the structure of our galaxy and things like knowing that this rock came from Mars, you know, and in between there are just all kinds of, it's a workhorse of chemistry and biochemistry labs everywhere doing all kinds of practical applications. So with that as background, it's truly my pleasure to introduce to you tonight's speaker, Dr. Douglas Barofsky. Dr. Barofsky is a distinguished scientist whose career has been dedicated to advancing the field of mass spectrometry, I should say. Dr. Barofsky. It's okay. There is a distinction, but I won't. Historical term, and it's kind of been used by astronomy lately, so you know, we'll let them have it. But Dr. Barofsky studied physics at Washington State University and Penn State University before earning his PhD in physical chemistry from the University of Bonn in Germany. And his groundbreaking work, I think this is amazing, began in 1965 when he invented and built a mass spectrometer while completing his doctorate studies at Penn State. He's a recognized leader in the field. Dr. Barofsky is a fellow of the prestigious Alexander von Humboldt Foundation in Germany. He holds an honorary PhD in ion physics from Uppsala University in Sweden and is an esteemed member of the American Society for Mass Spectrometry. And he was born in the Olympic Peninsula in Washington, but his roots trace back to southern Oregon coast, where he graduated as just one of 28 students from Gold Beach Union High School back in 1959. I'm not distracted at all. So please join me in welcoming Dr. Douglas Barofsky.
Thanks, Rod. It's my pleasure to be here tonight. And I want to go on the record. I'm in that kind of weird green category. Just to full disclosure, mass spectrometry, the science of weighing atoms and molecules. This is a topic of, let's see, I gotta get the right hand in. I want to start with a statement of the scientific method. The author here, excuse me. The author of this particular formulation of it is Richard Feynman, a preeminent physicist from the last century, a Nobel laureate. He stated it this way in a series of lectures that he wrote during that time, or co-wrote during that time. Observation, reason, experiment make up what we call the scientific method. The The talk tonight is going to dwell primarily in the experimental section, but I want to emphasize this is not just a process that goes from observation, reason, experiment. Okay, it can start at any one of these levels, go backwards, go around in a circle, crosstalk. But I thought this might be a nice way to start this talk this evening. Matter is going to be the, excuse me. Okay, I'm steady. Legs aren't as young as they used to be. We're going to talk a little bit, most of this talk is going to be about matter in various ways. So I wanted to start with the atoms and molecules and matter part. This is a statement of what's known as the atomic fact or the atomic hypothesis. All matter, mineral and organic, is made of atoms. And that is non-controversial. A corollary to that is nearly all of these atoms, at least on the Earth's crust in the atmosphere, are bound into molecules. So this is going to be the topic tonight of this particular lecture. Mass spectrometry is a ubiquitous branch of analytical science devoted to the invention, development, and use of instrumentation that can do a lot of things. It can determine the atomic and molecular masses with accuracy and precision. It can determine the identities or abundances of atoms in physical and biological samples. It can determine the structures and identities or concentrations of molecules in physical and biological samples. It's powerful and it's versatile. The term ubiquitous means that this technique can be used pretty much everywhere, and it is. It can analyze all the elements and essentially all the molecules. It can analyze samples in all states of matter. It doesn't matter whether our sample is liquid, solid, gas, or plasma. Samples can contain as few as 600,000 molecules. And you say, whoa, that's a big number. What do you mean few as 600,000? But in fact, 600,000 particles is just one atom, 1/quintillionth of a mole. A mole itself is a humongous number, 6.023 times 10 to the 23rd.
Wow.
If you study science like I have, that number is stuck in your head, you can't get rid of it. That's just a huge quantity number. So 600,000, say in a sample of a few milliliters of blood, and I'm looking for something in that blood, a drug or something like that, that's a very small number in that milliliter of blood. So this is a very powerful property of this technique. In the first half of the 20th century, the area of mass spectrometry, they called the original instruments called mass spectrographs, then mass spectroscopes, and finally mass spectrometers. It was basically an area of physicists. Physicists were busy inventing these instruments. Primarily, they were using them to make precise measurements of the atomic masses and discovering the isotopes of those elements. 2 Nobel Prizes came out of that. Early on, the father of mass spectrometry, or was known as the father, was a physicist from Cambridge in the UK, J.J. Thomson. He got the Nobel Prize for discovering the electron and determining its mass to charge. With instrumentation, I can't conceive of how he did this. A very brilliant student of his, Aston, was the first to really work hard on discovering the isotopes of these elements. And he was awarded the Nobel Prize in 1922 for that. There are 2 other Nobel Prizes from mass spectrometry that came in the second half of the century. But this was this chart, and filling in the information, and I don't know if you can see them well on this old chart, but these little numbers at the base of these elements down here, those are their atomic masses. And this was pretty much completed by the 1950s. And the reason I like this chart, it's old, it's dated, there are much better modern versions of it, but I like it because it hung on the wall of my science room in my high school. And for that matter, in the 1950s, it probably hung on the walls of of science rooms in pretty much every high school in this country, I suspect. But I thought it was interesting to show this. Whoops, I went backwards, didn't I? No, here we go. Second half. This is the era of chemistry, biochemistry, and molecular biology. Actually, just before the half century, in the late 30s and the 30s, chemists began to experiment with mass spectrometers, looking at gases, inorganic vapors, and stuff. It wasn't very much developed there, but by the end of the 50s, it really started to blossom. The technique began to be used very, very extensively by organic chemists. Very clever chemists worked out rules that enabled them to deduce the structures and molecular formulas from data they were acquiring with these mass spectrometers of that particular era. In the 1950s and the present, this is really my career, instrumentation and methods in mass spectrometry paralleled advancements in these particular areas here. Chemical extraction, separation, vacuum technology, material science, machining, electronics, and computer science. In fact, mass spectrometry, the development of the instrumentation and the methodology, was many times constrained because it lacked the technologies that were required for that. I wrote a proposal in the early 1970s. I'd invented a whole neat instrument and stuff. And I got reviewers that came back and said, this is impossible, that we don't have anything that can make this happen. And so it really moved along exactly with these other disciplines or technologies. The process of mass analysis really breaks down into three parts. Extraction. Atoms, molecules that exist in things, rocks, sludge at the bottom of a swamp, somewhere out in the ocean, smog up in the air, whatever. They have to be pulled out of there. We have to get them into a form that we can deal with them, in a solution, in some kind of a pot, so to speak. Okay? The next stage is separation. After we've extracted the molecules, we want to get them into a structurally pure form, if possible. That is, we want just deal with one chemical. Never happens, but we try. But we have ways to separate. I'll talk about these two things just very, very briefly. And finally, identification by mass. And the thing that I want to mostly talk tonight is how is it possible for us to determine the mass of little tiny things that we can't see, we can't feel. These are extraordinarily small things, and yet we're able to do this. And I think that's fascinating. It's certainly fascinated me for the better part of 60 years. So let's start with extraction. Most matter consists of an agglomeration of molecular structures which can be separated relatively easily by one or more stages of extraction. You all know extraction. This is tea. You've all seen the color extracted. You see the aroma that comes up. That's an extraction process. Very simple. These things you can buy in stores. Lemon, flavors, peppermint, almond, vanilla, whatever. These were all extracted from plants that have those essences with alcohol. This is a leaf with water droplets on it. The water droplets are extracting color pigments out of that leaf. In fact, I suspect a lot of artists in the past probably got their colors this way. Let's go to separation. After we've separated, oh wait a minute, I didn't say what I want to say here. This is a highly developed part of chemistry. If you go into a chemistry lab, there are apparatus, there are techniques for extraction that are highly, highly developed. Most extraction processes are done in 2 or 3 stages. They're done by circulating extractors. Ultrasonic agitation is often used to promote the process. Microwave, heating in microwaves is another thing. But it's a very, very, it's a science unto its own right, and the subject of maybe another lecture sometime. Separation. So once we get these things that have been extracted, we now have a kind of a family of molecules that have somewhat similar properties, okay? But they are distinct. They're chemically distinct by virtue of their structures and chemical properties. We want to separate them. Hopefully, we want to come down to a point where we are dealing with pure chemicals. The process that we do that by is usually called chromatography. Maybe a lot of you, maybe most of you, have seen this particular experiment in a middle school science class or high school class. You draw a band of ink on the end of a strip of white paper, you plop it into water, and all of a sudden you see these beautiful colors, which are what the ink is actually composed of, emerge. These are actually molecules that are in those colored bands that have structures that interact with light that produces that particular color. Now, this is called paper chromatography, and it's not very practical in the mass spectrometry world. We deal with primarily two forms of chromatography in the analytical world. One is called gas chromatography, the other is called liquid chromatography. Gas chromatography is used as these things. Now, it's hard for you to appreciate what these are. These are extraordinarily thin capillary tubes that are enormously long, anywhere from about 40 feet to over 300 feet long on these coils. They're hollow inside, they're tubes. And the tubes there's a solid material that's on the sides of these tubes, and when molecules move through them, they move at different paces. We start the experiment at one end of these things, we'll force an inert gas through there, maybe helium, maybe nitrogen, something like that. We'll put a plug of our sample. This will be a gas, so it would be inserted from a gas containing tube or something like that. But just a plug of that, and then train it into this carrier gas. So all the molecules in that sample are starting at the same point. But as they move down this enormously long capillary, they spread out. They have different sizes, they have different shapes, they have different electrical properties, until they separate. And at the other end, out pop usually fairly pure chemicals. Okay? Another form, liquid chromatography. Liquid chromatography is performed in these stainless steel cylinders. There are big ones and middle-sized ones. Those are used for preparing pure samples of one chemical. Okay? You put a batch of something at one end, they go through this chromatography thing. What comes out the other end is a pure chemical of some sort. The little ones, the ones at the bottom here, they're very tiny. They're about a little over an inch long to maybe as long as 10, 11 inches. The inner diameters of them are only 2 to 5 millimeters. They're packed with little tiny beads, very tiny things, about 1.5 micrometers in diameter up to about 50 micrometers of diameter. 50 micrometers is something you're very familiar with. That's about the average width of a human hair. Okay? So you can imagine the insides of these little particles are pretty tiny. Again, we put sample in at one end. Now we force it through this packed column with pressures that are range from about 700 to about 20,000 pounds per square inch. These are enormous pressures. The weight of this atmosphere on us exerts a pressure of 14.7 pounds on every square inch of our body. In fact, every square inch of everything in this room. Okay? We can deal with that. We could not deal with these pressures on our bodies. They're very high. But the same process occurs. Molecules move along, they begin to separate because they have different sizes, different electrical properties, different shapes, whatever. Okay? And they pop out the end more or less in pure forms when they come out the end. So next, we're going to talk about the difference between weight and mass. I suspect this audience is pretty much familiar with this. Female Cocker Spaniel on this earth is going to weigh something like about 25 pounds. 111 newtons if we use the international system of force. This weight, what we call weight, is actually the action of the Earth's gravitational attraction toward us. Okay? So it gives us this sensation of feeling, but it's actually the force acting on the mass of that dog. If we go to the moon, you probably all know this, the moon has about 1/6 the gravitational pull that we have here on Earth, so our little copper is going to weigh 4 pounds. But look at her. She's no different. She's the same amount of stuff that's in that Cocker Spaniel, okay, whether she's on the moon or the Earth. This is mass. Mass is the stuff that matter is made of, okay, the amount of matter in an object. Our little copper is 11 kilograms on the Earth, she's 11 kilograms on the moon, she's 11 kilograms wherever we want to put her in the universe, providing she doesn't get burned up or something like that. Assuming she remains in a stable form, she's going to be 11 kilograms. Each of you have a mass. I have a mass. Okay? It's the material that makes us up. Okay? The matter with which we're composed. Let's look at the atom. The atom has a core. Again, I'm probably lecturing to the choir here, but let's just review what the atom is. It has a core. The core is made up of 2 particles. Neutrons, which are electrically neutral, protons, which carry positive charge. Circulating around the nucleus are electrons, and they're negatively charged. They carry negative electric charge. This is a very inaccurate picture of the atom. The electrons are kind of swirling in clouds, so to speak, and the neutron itself is a tiny thing. The atomic diameter, that is the diameter of the cloud of the electrons, is on the order of about 10 to the minus 8 centimeters. This is a very small dimension. This is 10 nanometers, 10 billionths of a meter, okay? Such a dimension we can't feel, experience, we can talk about it, physicists can measure it and do it in calculations, but it's a tiny, tiny thing. 100,000 times smaller than the diameter of the atom is the nucleus. 10 to the minus 13 centimeters, okay? An exceedingly small thing. If we could blow this thing up to something about the size of this room or twice the size of the room, the nucleus would be just a speck in the middle of the room, which we might barely be able to make out with our native eyes. Now, there are properties to atoms that I want to emphasize because they're important in mass spectrometry. This is the simplest atom that there is. 1 proton is the nucleus and 1 electron going around it, hydrogen. This has another form. We can add a neutron to the nucleus. This is a form of hydrogen called deuterium. It's chemically the same as hydrogen. The chemistry of atoms is determined by their electrons, not their nuclei. But the weight or the mass of an atom is determined by its nucleus. So the deuterium atom has twice the mass of hydrogen. We can go a little further. We can add another neutron to this thing. Really bulge it out, if you will. Okay? This is called tritium, but it's still hydrogen chemically. Right? But it has 3 times the mass of our hydrogen. When we squeeze 2 atoms together, close together, they can form molecules. They bind to each other. Again, this is a very inaccurate picture, but it conveys the idea of what's happening. They get close enough together, and the electrons begin to reemerge, or rearrange themselves, excuse me. And so you get something that looks kind of like this, and we call it a hydrogen molecule. Now, in reality, those electrons aren't sitting just right there between the 2 protons, okay? They're still swirling. But they spend more of their time now in between the 2 nuclei than they spend in the space outside of them. And if you will, that's the glue that forms a chemical bond. And it doesn't matter where it's small as hydrogen or something, some other bigger element, it's the same thing. The picture of the electron is a little more complex, but basically this is chemical bonding. Now, to analyze these things, we have to ionize them. That is, we have to electrically charge them. Because the handles we can exert on these things are electric and magnetic forces. I'll talk about that in a minute. But we have to do something to this thing to make it electrically charged. Not hard to do at all. We'll just take out an electron. okay? Now we got 2 protons, both plus charge, 1 electron negative. There's an excess of positive charge. This is a positive hydrogen ion. So when we're talking about ions, we're talking about atoms from which electrons have been removed or added, okay? Let's add an electron here. Whoa! Now we got a negative hydrogen ion. More negative charge than positive charge. Very simple to understand in this simple thing, but this can do this to any atom, any molecule. We can take out electrons, we can add electrons. If we really want to get fancy, we can even do this with protons. Let's leave it at electrons for the moment. Now we want to talk about how do we actually determine the masses of these in an instrument. Remember, we can't see these things, we can't touch them. They're godly small, unimaginably small in our minds. Every little speck of space around us has billions of these things. Remember that Avogadro's number, an uncountable sum of these things. But we can isolate them, almost get them to individuals for a purpose. Now we're going to take advantage of the fact that they're charged particles, and we're going to use electric and magnetic fields. Ion optics itself, mathematically, is a little complex. I've actually toyed, and I had a slide, and I was going to start out with a set of equations called Maxwell's equations. Very sophisticated form of mathematics. Some of you are laughing, you maybe know what these things are a little bit. I decided that ain't going to work. So what we're going to do is, I'm going to give you kind of a basis set, 5 devices that can be combined and arranged in different ways to create a mass analyzer. Start with the first one, an electric accelerator. We take 2 plates, metal plates, we attach a positive terminal of a battery to the bottom plate, a negative terminal to the top plate. Inside is a space that we call an electric field. All right, this is a kind of an abstract thing in physics. It's, again, complicated mathematics, but it has a direction, and it's, when you put, it goes from a positive charge to a negative charge. If we introduce a positive ion in the bottom of this thing, it immediately experiences a force in this electric field pointing upward, whoop, shoots out that hole. It accelerates. It makes an electric car, the acceleration of an electric car, look like a piker. This thing gets out of there in milliseconds, actually in microseconds, thousands of seconds. The thing that I want to point out, though, that's important for this lecture, the speed, there's an equation for that. But I don't want to dwell on the equation. I just want you to know that this speed depends on this particle's mass divided by its charge. This is called mass to charge ratio. Mass divided by charge. Okay? And it depends on that. Let's go to the next guy. A magnet, a horseshoe magnet. Okay? South pole at the top, north pole at the bottom. There's a thing called a magnetic field in between the space between these 2 poles. It always goes from north to south. I don't know who determined that, but there it is. We take our charged particle, a positively charged ion, we shoot it sideways in here. You think, wow, why doesn't the bugger just go right on through? The magnetic field does a strange thing here. The force on the particle is sideways, out of this thing. And so, whoop, it comes out over here, at an angle. If it were a negative ion, it'd go whoop, into the back. Okay? Important thing for you is that the deflection depends on the mass divided by the charge. Mass to charge ratio. 2 particles, different mass, different charges, or both, are going to deflect at different angles. So we can tell them apart. Okay? We can measure those angles and tell them apart. I'm not going to tell you how we measure the angles, but we can. Okay? Accept it. Let's go to the next one. Here's the next one. There. This is an electric deflector. Okay? In this case, we've got, again, 2 metal plates, one above the other. We attach the positive pole of the battery to the top one, negative pole to the bottom one. We shoot our ion in here, sideways again. Okay? Whips through here. Because it's positive, it's repelled by the positive charge in the top plate, it's attracted by the positive charge in the negative plate, and it bends down. If this were a negative ion, we shoot it down here, it bends up. Important, the carry away message is that the deflection depends on the mass divided by the charge. I think you're getting the idea now, okay? We can measure these angles, and we can tell two particles that have different masses, different charges or both. We can tell them apart, okay? The next one's a little more difficult to grasp, but I'll try to get the idea through. We have in 4 plates. In actuality, in most instruments, these would be rods, but this is good enough. They can be anything from a couple inches long to as much as a foot and a half long, okay? In this case, we're going to apply voltage on opposite plates again, but it's not going to be a static voltage, it's going to be an oscillating voltage. AC, out of your wall. AC, though, out of our wall is only 60 cycles a second. That is, the voltage fluctuates 60 times a second. In our case, we're going to use radio frequencies. Think of your FM tuner. 90 on the dial, 101 on the dial. What you're tuning in is an oscillation of 90 million oscillations a second. 103 oscillations a second. So this is just an FM dial, or a radio FM dial. We do the same on the top and bottom plate. We send our charged particles through there, and they dance. Oh, do they dance. They do wild stuff. Now, believe it or not, there are mathematical equations that you can draw this from, okay? They're called Lissajous figures, and you can find mathematical forms for them. The point, though, is that the choreography of the dance is determined by, you guessed it, mass divided by charge, okay? So we tune these frequencies a little different, and this becomes a filter. We can let particles with one mass to charge through, tune it differently, particles with different mass to charge go through. Mass analysis. One final case, ion cyclotron resonator. Dr. Price knows a lot about these things, but this is a tiny one. Okay? We have our 2 plates over here. Again, we connect them with this FM radio frequency, okay? Millions of oscillations per second. We put in a magnetic field here. Now, I'm not showing the magnet, but the North Pole is going to be down here, the South Pole is going to be in the back. The magnetic field goes through it, all right, from North Pole to South Pole. We inject a charged particle in here, and it spins. Oh my, does it spin. Millions of times a second it goes around this circle, right? When a charged particle moves, it becomes a kind of a broadcast thing. It sends out a radio wave, all right? These 2 plates on the top are our receivers. They pick up this oscillation of this thing spinning around in here. Comes out here, so we put a radio tuner there, pick up the frequency, and my God, it depends on the mass to charge, okay? So 2 particles spinning in here that have different masses, different charges, different mass to charge ratios, different frequencies. We can tell them apart. So we put all these things together to create a mass spectrometer. Now I'm going to show you 3 mass spectrometers that are not the most typical, but I think they're fascinating. The upper one is a mass spectrometer that you can hold in your hands. This is coming. This is the future right now. They're being developed for all kinds of field work. Environmental scientists in the field can use mass spectrometry now directly. The military loves these things because they can, trace explosives and things like that. The place where I think they're going to be most interesting is if you have the unfortunate chance to be in a hospital bed, you may, not too long down the line, have one of these sitting right by your thing here, so that they can check, administer, or confirm that the medication that's being administered to you is what it really says on the bottle, okay? As you know, errors in medication administration can be very deadly. This little guy, and it is a tiny, tiny guy, is a moon mass spectrometer. It's out there right now roving around on Mars, or one like it, okay? They come in all sizes and dimensions. At the opposite end is this gigantic thing. You remember that accelerator thing that I talked about just a few minutes ago? Well, the battery on this one's 3 million volts, okay? It is a big machine. There was privilege when I was in Sweden at Uppsala University working with one of these instruments. They're primarily used to analyze elements, not molecules. These are the kinds of mass spectrometers you mostly see in a typical laboratory, right? They have designer clothes on them. I don't like them. You don't get to see the stainless steel tubes and the wires and all the neat stuff that's underneath these things. But they're amazing machines. And they come also in different sizes. They come in sizes that you can put on a bench top, like here and here. You'll notice that some of them have GC, GC, or LC, LC attached to them. They come complete with chromatographs, liquid chromatographs or gas chromatographs, depending on the types of samples. I can tell you that the heart of this thing is an invention that I did with my professor at Penn State back in the 60s. I can tell you that this thing I'm a co-inventor of in the earlier form when it was laying down sideways. These are just amazing guys. Let's summarize where we are at this point. We've extracted some stuff, okay? We've separated the molecules in that stuff. At that point, before we put them in the mass analyzer, that's when we ionize them. And we do nasty things. We put them in electric discharges, we whack them with lasers, beams, we whack them with ion beams, we slam atoms into them, we even slam them into some things, or walls or stuff like that, just to get those dang electrons out. They don't come out always willingly. If we want to add an electron, that's a more general process, but the ionization takes place, then they come out and go through these mass analyzers. And all these things inside are just basically some kind of combination, some clever arrangement of those 5 devices that I showed you. Okay? So they come out. Now, who says, the mass to charge right? We got computers today. Back in my day, we used rulers and rubber bands, but now we got computers. And the computers do the job. They know what the dimensions of these instruments are. They know the frequencies. They know the voltages they're tuned to. So the computers turn that all into mass to charge. And we plot it out on graphs that look like this. So down here, on this axis, we have mass to charge ratio. Okay? And the computer's done that job for us to convert whatever it was, a frequency or something, into this. You'll see signals. Okay? And we give these different signals. The molecule that we're probably trying to analyze, the main peak in one of these spectrums is going to be what we call the molecular ion. Okay? It was the molecule that we were tuning to. It's lost, it's our molecule of interest, it's either lost or gained electrons. Things break off it. Okay, that ionization process can really knock stuff out of the molecule, and so we get fragment ions, okay, pieces. These are important because these fragment ions actually can be related back to the molecular ion here. Remember I said those clever chemicals worked out ways to deduce the structures of molecules? Well, they did it by learning how they fragment. So first they learned how they fragment, and now when we see these fragments, we know how to put the molecule back together. Okay? And then there's these dang isotopes, these little satellites. Okay? A big molecule has usually hundreds of carbons in it. And the carbon comes in 2 stable forms, mostly carbon-12, but there's a lot of carbon-13. So if you get a molecule or 2 that's got a carbon-13 in it, it appears as a satellite. It's one mass unit or one proton a little bit heavier, okay? Might even have 2 of these in it. In fact, when they're really big molecules, you'll see actually an envelope here, and you'll see these isotope peaks all over the place. So this is the mass spectrum. This is what we get out, and this is what we interpret. So let's see how it's used, okay? I asked the board of this club, I said, gave them this list, and I said, I don't know how to choose here, what am I going to talk about? Okay, what am I going to show you? Well, they picked 3 for it. They picked geochemistry, pharmacy, and forensics. So I'm going to show you an example, a little bit of example, of how mass spectrometry is used in I'm sorry, you hearing me? I'm walking away. You know, when I talk in front of the platform, I like to walk through here. I'm dynamic. I wave my arms and do stuff like that. Chaining me to this microphone is not my style, but here we go. So let's look at geochemistry first. And geochemistry is an enormous field. There are at least 20, 30 different ways mass spectrometers are used in this field. I'm going to pick on one called oil fingerprinting petroleum, okay? Because it's something I think you've read about in the newspapers, and you may say, how the hell did they know that? Or how did they know this? Most likely it's always a mass spectrometer behind it. Crude oil originates from biological organisms. So back here, a few billion years. In fact, by dating using a mass spectrometer, we now know that the age of the Earth is 4.55 billion years, plus or minus about 70 million. Okay? This is an old rock we live on. We now know that some of the latest things, just this last year, they found fossils of single-celled critters that swam around, okay, over 4 billion years ago. In that first 500 million years of the life of this planet, life was already showing up. Okay? At any rate, these guys die, they fall in the bottom of the pool or the pond or the sea or the ocean that they're in, and they form layers. Over billions of years, those layers build up. And then they go through hell. They get ground up, they get heated up, all the geological processes that preceded what now exists, what we actually walk around in and on. And temperatures, the ground, the pressure is enormous, and eventually they pop out as petroleum, crude oil. Okay? What's really fascinating is the fact that molecules that made up these guys billions of years ago, even through this horrific processes that end up being crude oil today, all right, some of those chemical features are preserved. Now, these are chemical structures. So basically the chemist's way of showing how carbons are all connected, all the points and stuff are here. I don't expect you to understand them, but you can see this pattern on this thing up here. This is chlorophyll. Okay, and there's a pattern of structure up here. It's kind of square, and it's got these little hexagons in the edges and the corners of it. Through all of this process, that structure is actually preserved. And it comes out of the crude oil today. Here it is. Okay, if you look at this pattern, it looks just like that up at the top. This can be traced back to these guys back here. Okay? That's called now, they've given it the name, petroleomomics. Okay? That is actually deducing what the living forms back billions of years ago, okay, look like from the chemistry of some of the things we can find in these oils. Now, how do we get this? Well, the mass spectrometer gives us that structure. Okay? So, this is that word, I think, did I put it in here, petroleomomics? No, I didn't. At any rate, so this is the basis of studying petroleum with mass spectrometers. We can learn from that the source it came from, the types of rocks that it came from. We can learn the maturity, the age of the oil. We can learn how it migrated in the geological layers over time. And what I want to emphasize right now is we can use this as a kind of a fingerprinting to trace oil spills. This is a map. Most of you recognize it. It's the southeast United States, Texas, Louisiana. These are all oil fields here producing petroleum. Out here are oil rigs out in the Gulf of Mexico. Oh my God, it's the Gulf of Mexico. You didn't catch me. Where's that? Here we go. Already. It's going to change things here. Anyhow, samples were taken from all of these. And these are mass spectra of them. Now, if you look at those things and you think, oh my God. Qualitatively, though, you can easily see that they're different. So if I have a sample of petroleum, and it comes up with, say, this thing here, and I say, oh my God, that came from where did it come from? Can't see right there. That may be a Gulf one, I'm not sure. Anyway, it doesn't matter. They knew. All right. This study actually was just done 4 years ago. It was published in the Journal of Environmental and Geological something or other. And then I just happened to pick it up. But this is basic. This is how simple it is to fingerprint. Okay? When you look at our own fingerprints, they're just swirls and stuff like that. Well, the mass spectra just become that easy. But your eye can easily tell the difference. And of course, now you attach this to a computer, and you really get differences. Here's an example of a high-resolution mass spectrum of South American crude oil. It contains 11,127 signals, mass peaks. At the time it was recorded in 2005, it was the most complex chemical mixture ever resolved and identified in a single mass spectrum. If we took this, it was on some kind of a rubber band or something, and we could stretch it the length of this room, probably twice the length of this room, we would see detail down in that mass of things that would look like this. This was a very high-performance instrument. It was able to resolve these individual molecular structures in this crude oil. This particular peak here are separated by 3.4 thousandths of a Dalton, or a proton, the mass of a proton. Okay? That's a difference chemically between 3 carbons, or 1 sulfur and 4 hydrogens. That is a little feature that could be, I don't know how to do it, but these guys, the geochemists, can relate that back maybe to that critter that lived 4 billion years ago. Anyhow, they dig down this deeply into this stuff to get information that we can relate to, learn something about what happened somewhere in Europe. Ultra high resolution mass spectrometry, the same thing that was done here, was a big factor when this damn thing happened, the Deepwater Horizon blowout in the Gulf. There it is again. God dang. I'm going to have trouble in the future. At any rate, as horrific as this disaster was, so much was learned about mass spectroscopic studies, how to interpret oil spills of this magnitude. I'll give you just 2 quick examples. Furnace oil released during the 2014 Bangladesh oil spill, using techniques developed up here in the Deepwater Horizon incident, were traced to the Middle East. Oil deposits found on the coast of Brazil, actually a huge length of the Brazilian coastline, in the summer of 2019. This was quite relatively recent. I remember reading about it in Science. Anyhow, those marine, they were traced back to bunker fuels. These were spills from ocean-going ships that use this bunker fuel to power their diesel engines. Somebody out there really spilled it. I don't know if they ever actually traced it back to the ship that had the spill, but it made a mess in Brazil. Okay. It's kind of like the oil spill up in Alaska or something, only this happened out in the ocean. So they can stick their heads in the sand and say, we didn't do it, but eventually they'll probably find it. Drug discovery. Let's go to pharmacy. In the history of medicine, how am I doing time-wise? I may be way over time.
Good.
Huh? I'm good?
You're good.
Okay. History of medicine. The source of medical products has been plants, marine organisms, or microorganisms. Things that grow down in the dirt and whatever. Okay? Indigenous people knew this. They've used medicines for years and years. They didn't have Nazi names like we give them today, but they were very savvy about these things. Turns out that still about 40% of the medicines that we use today are extracted directly from these living organisms, this life. Okay? Pharma, big pharma, okay, comes into the picture because they use mass spectrometry to deduce the structures of things that come here. Once they know these structures, then organic chemists can go in and dicker with them. They can add things, take things away, whatever. They do that attempting to improve activity, reduce side effects. Today, a big activity is to stay ahead of mutant forms of bacteria and viruses, okay? But mass spectrometry guides this whole process. Now, I tried to find examples that would be easy to present and understandable, but the chemistry is very complex, difficult to get. It turns out, though, there was a case in my own laboratory in the mid-90s that I want to show you. This is paclitaxel, is the active ingredient in Taxol. Some of you may know about Taxol. Okay, it's found in yew trees, both native to this continent and Europe. Taxol, it's been approved for cancer treatments for quite a long time. The principal ones, particularly for women, are ovarian and breast cancers. In the mid-1990s, a colleague of mine at OSU in the Department of Horticulture, a man named Larry Daly, walked into my lab, actually my office, and he had a little vial and he had a sample in there that he and a student had been extracted and partially purified from hazelnuts. He thought that there was Taxol in it. He was very convinced by a bunch of chemistry tests that contained Taxol. So we did the mass analysis. This is a mass spectrum that was produced in my laboratory, gas or liquid chromatography mass spectrometry. Okay. We knew the structure already of Taxol. So this structure we already knew. So we could rationalize the appearance of these peaks. And by God, they all fit right into this structure, okay? We had the chromatography. So we, almost at this point, were certain that we had Taxol, but we went one step further. Larry Daly obtained a sample of authentic Taxol from Bristol Myers. Bristol Myers was the big pharma that had the franchise on this. Probably still does. But this is our mass spectrum. This is the mass spectrum of our sample from Bristol Myers. You can look at them and you'll see that almost all of the features match up. So this nail was a nail in the coffin. We knew that we had, or Larry knew that he had Taxol in his sample. In the mid-90s, a single Taxol treatment cost about $1,000. I have no idea what it costs today, but I'm guessing more. Larry had the idea that he could extract Taxol from hazelnuts and reduce treatment costs. And he wanted to explore this, the feasibility of this idea as a commercial product. He sold it to the hazelnut growers here in Oregon. They gave him money. Bristol Myers wouldn't give him the time of day. So the story ended there as far as I know. But right here in Oregon, we have a supply of Taxol that could substantially reduce the thing. We discovered that with mass spectrometry in our laboratory. Forensics. The first ever mass spec lab, forensic mass spec lab, was established in Birmingham, England in 1973. And their first year was busy. They did all kinds of stuff. 59 cases involving illegal possession of drugs. 47 suspicious tests. That's CSI stuff, right there. You know. 18 explosives, and so on down the thing. They had down here documents and knowledge. I don't know what that was, but they were very busy that year. Since that time, forensic labs with mass spectrometers have just sprung up. I don't know what the number is. I'm guessing in the thousands, just in Europe and this country alone, maybe more. I look for things that I can present to you, and again, it's just too complex, okay? Two things, but I came up with one I thought maybe be of interest to you. It's a incident of historic fraud, and some of you may be familiar with this. The Shroud of Turin. This is a linen cloth believed by many Christians to be Jesus Christ's burial shroud. Okay? It showed up in 1354. Remember that date, 1354. It started appearing, it says here, somebody began to exhibit it in this little church in north central France. In 1683, it was transferred from that church to the Cathedral of St. John the Baptist in Turin, Italy, from which it now gets its name. Okay? In the 1980s, I don't know who conjured up this idea, but all attempts to age this cloth and establish its origin, okay, had really failed. They were questionable, they were debatable, they weren't convincing. So somebody got the idea, well, let's date this using that form of mass spectrometry I showed you earlier, the accelerator mass spectrometer, the 3 million battery guy. Okay, so 4 of these instruments were selected. One in Rochester, University of Rochester here in this country, University of Arizona in Tucson, Oxford University in the UK, and I'm not sure what the institute was in Zurich. They were well separated. They had no collaboration or interaction with it. They were performed to do carbon-14 dating. They didn't have to use uranium lead dating. They weren't going back billions of years, at the most 2,000. The experiments were conducted very strictly under controls. Each laboratory received 4 samples. 3 of them were kind of standards, and 1 of them came from the shroud. Okay, but it was blind. They didn't know which they were analyzing. Amazingly, when they were all said and done, they averaged the age that they had determined for this, for the linen in this shroud. They came up with 691 years, plus or minus 31. That's enormous precision. Okay. Well, that places this, the origin of this shroud somewhere between 1260 and 1390. Remember the number 1354? Nailed it, right on the button. The shroud is medieval. Doesn't even get close to the time of Christ. I'm going to leave with one other example. This is an unfinished business. So I'm going to leave you here with a little question. Not too long ago, in 2000, this fossil from a Tyrannosaurus rex was found. It was dated to be 68 million years ago. That's the period of the dinosaur. Nothing unusual about that. But this sample was a little bit unusual because it contained some soft tissue. It was inside the bone. So somebody said the idea, oh, let's analyze that by mass spectrometry. Okay? And they did. And part of the analysis was protein analysis, and they found structures of protein in there that said that it's probably collagen in this bone. Now, collagen is a very common protein found in bones, very specifically birds, and very specifically chickens. So I'm going to leave you with this question. Was Tyrannosaurus rex just a big rex? Now, you guys know the scientific method. Where would you go? How would you deal with this? All right, folks. If you have questions, I'll be glad to answer.
Yes. I managed to graduate from college and every week take a chemistry class and hurt my brain tonight.
Physical chemistry class?
No, I never took chemistry.
Oh,
Yeah, so
physics.
what is the difference between DNA and mass spectrometry? What I saw there was like, let's kind of DNA of oil.
I still don't get the question. What's the difference
Between DNA and mass spectrometry.
DNA?
DNA.
DNA and
Yeah.
mass spectrometry?
Because they seem similar.
DNA is the genetic stuff that's in every cell in our body. You can use mass spectrometry to analyze it, and we have. I've worked on a lot of DNA projects at different times. But DNA is a molecule, a very specific molecule. Actually, we're made up, we have 3 big, long, or what are called biochemical polymers that we're made up of. Proteins, DNA, and then sugars, carbohydrates, long, thick ones, bigger than what we eat. All of those can be analyzed and are being analyzed as I speak here by mass spectrometry. Okay? So they are the subjects of analysis by mass spectrometry. Okay? Mass spectrometry is a tool. There is no single instrument that is the mass spectrometer. As I showed in the pictures, they come in all shapes and sizes. Okay? But somebody is analyzing DNA right as we speak. Actually, some buddies, all right, by mass spectrometry, for certain. More questions? Yes?
So I'm picturing if you wanted to analyze a sample of a delicate, complex organic molecule, but then you have to ionize it. And as you said, that's brutally, bombarding it with lasers or heat or some form of energy to pluck off an electron. How do you know you're not damaging the sample so that you're looking at something other than what you expected to be looking at?
That's a very, I like this because everybody always says, that's a really good question. But it is a good question. It's a very important question. Starting way back when, actually at the time when I got into this business, there was a quest really to find gentle ways to ionize biological molecules. In fact, the thing that took me to Germany was to start learning about biochemistry and seeing what I could do to contribute to the development of mass spectrometry for these things. The first big problem was how to make these elements fly. As I said, proteins, carbohydrates, DNA, these are big, big molecules. And if you try to roast them or vaporize them or something like that, they just fall apart. There's no way you're going to get them up flying. You've got to get them up into the air so you can get them into a vacuum system. You've got to take these electrons off them or add protons to them. So actually from the period of about 1970 up until 1980, okay, many physicists and chemists like myself were working with different ways. We all wanted to invent that thing. And in fact, it resulted in the Nobel Prize, ultimately the solution, in the early 80s. Okay? The way it ended up being was two ways, actually. One, you could entrap these molecules. You did the extraction, you did the separation, okay? And now they were in a solution. And so what you did is your proteins or DNA, you sprayed it out, all right, in an aerosol spray. So the molecules were trapped in little tiny droplets of solution. And you did this in an electric field between two charged electrodes, so the little droplets had charge. When they evaporated, the charge came down on the protein or the DNA, and it was still intact. And so these elephants, we could get them to fly that way. The other way was a little different. The proteins or DNA or the big molecules were meshed in a material, it turns out an organic material, a filter kind of a material, all right? They were placed on this, and this is really counterintuitive. You slammed into this thing, with laser beams that would just knock the shit out, pardon the language. It would just blast these buggers apart. But what happened is they created little plasma tracks in this material that they were sitting in. And out on the fringes of that, it was gentle enough, and they floated out with this matrix material. And so again, they were up in the air. And they caught a few electrons or protons in the process, so they were ionized. We can capture them, send them down our mass analyzer. And that ability to be able to analyze these big, big organic molecules, as I say, that it resulted in a Nobel Prize. We had a conference on boats in the Mediterranean, out of the southern coast of Côte d'Azur of France. Danish colleague of mine and a French colleague of mine were very eminent physicists, and one was a biochemist. They were both superb sailors. They had this idea we could have a conference and sail out in the Mediterranean at the same time. We did. It was a marvelous conference. There were about 80 of us there. 2 of those people were Nobel Prize laureates in the future. Okay. It was a powerful conference at the time. We struggled with this, and I was privileged to be part of this process. Okay. When they get them into the mass spectrometer, though, we do want to break them up so that we can put them back together and see how they're built. Okay? One of the instruments that I invented made that possible, break them apart. And another way is adding electrons to them. I've also invented a part that makes that possible. So dealing with these things has been really fun over the years. More questions? Yes, in the back.
What's the role of the Fournier transform? What's the role of Fournier transform in these instruments now?
I'm sorry?
The Fournier transform. Fournier
Do
transform.
you use Fourier transforms at all?
Huh?
FTMS.
Do you use Fourier transforms?
Yes. I didn't personally, never actually use those instruments. We had one in our lab at Oregon State University. They're called Fourier transform ion cyclotron resonance. They're an analyzer of that cyclotron device that I showed you, a little more sophisticated. Actually, I showed you a picture of one of those instruments. They're immersed in a huge tank of helium. Okay? The mass spectrometer is about that big inside there. When those charged particles spin around in that cyclotron box and they radiate, okay, and that signals are picked up, those are frequency signals. Nothing weak looks like that. So you have to do a mathematical transformation on them. You know what it is. It's called Fourier transform, and it converts those frequency signals to guess what? Mass to charge.
Thank you.
Okay?
You know, perhaps Dr. Barofsky would be willing to take a few more individual questions, and we can let the rest of the audience make their way home on Tuesday. You can dream about flying elephants or whatever else you like. And on your way out, please don't forget to stop by and talk to Jocelyn about helping out on Thursday. But before anyone can leave, I think we need to thank Dr. Barofsky very much.